Alright, welcome back everybody. Before we begin, we have a little housekeeping to do. We're going to do Ito's lemma, and so we need to know all these processes, all their squares, and all their cross terms. But I did forget in the first video to use the price of risk to further simplify the wealth equation. So if we expand out this term in the middle here, we'd factor through that RT. So we get RT minus pi t RT plus pi t mu t. And then from our price of risk equation, we can rearrange that to get an equation for mu t is equal to sigma t lambda t lambda t plus RT. Yeah, okay, and then we'll plug that in. So we get RT minus pi t RT plus pi t sigma t lambda t plus RT pi t. And then that cancels with that, and then we're left with RT plus pi t sigma t lambda t. And so our wealth equation, I'll erase this to make a bit of room, becomes dW equals WT times RT plus pi t sigma t lambda t dt, and then the rest stays the same. Yt minus ct dt plus Wt pi t sigma t dzt. Okay, this can all go away. So I've done all of the cross terms and things. The only things to note here are first quadratic matrices. You're going to get this flip-de-flop. So when we do pi times pi, you get pi transpose times pi, and then in the middle we're going to have this covariance matrix, sigma transpose sigma. So that's that. And then we can also, this thing here, v transpose v, v hat x squared, we can also define this as sigma t of x. We'll call that sigma x of x. So that'll just be a little less writing. Okay, so our job right now is to find mu, what we've called mu of j. Mu of j. And mu of j, remember, is going to be equal to the drift term. Drift term of dj. So what we need to know is we need to know what is dj. Let's give ourselves a little bit more room here. We need to see that stuff. Okay, what is dj? dj is the partial derivative. So j is a function of three variables. Let's write that down to be clear. And we need to take partial derivatives of all of them. So we're going to have three first order derivatives. So partial j, partial w, dw, plus partial j, partial x, dx, plus partial j, partial t, dt, plus 1/2 times every possible cross term. So we have three variables, and so we have a bunch of cross terms. We have ww, we have wx, we have wt, you know, we've got 9. But remember that these middle cross terms, this and this, are the same. So that's important because we have to make sure, and TW, sorry. We have to make sure to put 2's in front of those. So we're going to have 9 cross terms with some 2's in front of a bunch of them. So let's do it. We have partial j, let's just do the doubles first. Partial squared j over partial w squared, sorry. dw squared plus partial squared j over partial x squared dx squared plus partial squared j over partial t squared dt squared. And then we'll do the cross terms, and we have 2 of each of these. So we're going to have partial j over partial x partial t plus 2 partial j over partial w. Let's try to do this more organized. Let's do x and w plus 2 partial j over partial w partial t. And that should be everything. So let's just make sure we did all the doubles. We did xt, we did tx, we did both of those. We did tw, we did wt, we did this one. Okay, good job. Good job, us. So next we need to decide what is use, what don't we need to do. So this is not 0. So we're just going to make 2 categories. This is not 0 because it does have a z term. This is also not 0. It has 2 z terms. This is 0 because it's just dt. X and t, this is 0. X and w, this is not 0. And w and t, this is just 0. So not the worst. Could be worse, I think. Okay. So let's write down all of our partial derivatives. And I'm going to start using the notation that Professor Glachon uses. So the j with the little subscripts to denote derivatives. So this is going to be j of little w, and then the dw, which I have handily written down over here. Wt times rt plus pi t transpose sigma t lambda t. I guess I made a mistake when I multiplied that through earlier. I apologize for that. There's been a lot of that in these videos. I shouldn't be making these at 1 a.m. dt plus wt pi t transpose sigma dzt. Okay, plus our j of x, and then the dx, which is just mx dt plus vx dzt plus v hat x dzt hat plus jt dt. That's a nice one. I like that one. Okay, so our not zeros, we have our dw squared. So plus 1/2 jww. And w squared will be w squared t pi t transpose sigma t pi t. And then we have not 0 is the x cross, so plus 1/2 jxx. And then x squared is just going to be that sigma x xt dt. And then our last one is this, so this we have a 2, so there's no 1/2, and it's going to be the jxw. And that one is v of x wt pi t transpose sigma t dt plus v hat of x. There should be a bracket here. V hat of x wt pi t transpose sigma t, can I do it? dt. Okay, not the most beautiful thing in the world. I suppose I forgot to mention that when we cross multiply x, that dt, dz and dz hat, where are they? Here, dz and dz hat are going to be equal to 0, just because they have 0 covariance. And then dt dz and dt dz hat are both going to be equal to 0. Sorry, those are both going to be equal to 0, but then this dzt and dzt hat we're going to assume is just equal to dt. And I'm assuming that to get the correct answer. The thing about independence, I mean, that makes sense to me, but that doesn't get the right answer, so here we are, you know. Okay, so let's rearrange this mess, this big pile of stuff into the dt and the dz terms. So if we sort it, we're going to get jw wt rt plus pi t sigma t lambda t d. Oops, we're not writing dt yet. Plus yt minus ct. Okay, and then we also have, let's put another big bracket here, plus our jx mx plus jt plus 1/2 jww wt squared pi t transpose sigma t pi t plus new line 1/2 jxx times our sigma txx plus jwx. I hope you're all watching this on like times 1.5 or 2, because man, pi transpose t sigma t dt plus the stochastic part, which will just be, and there's two stochastic parts, we have a dz and a dz hat. Yeah, we have a dz and a dz hat. So we're going to get jw wt pi tt sigma t plus jx v of x, and that is our dz term, and then we have one lonely sad little dz hat, which is just jx v hat of x dz hat t. Okay, but we only want the drift, so go. This is all gone. Go away. And actually, we're going to divide at the end by dt, if you remember, so that actually goes away too. Okay, that's great. So let's plug that back into our Bellman equation and achieve what we were hoping to achieve this video. So if you recall, we had j of wt, xt, and t, and that was times delta, is equal to the maximum of ct and pi t, and then u of c, plus all this junk. And actually what I'm going to do is I'm just going to copy paste it, and after I do, that will be the end of the video. So if you are not keen to sit here and watch me slowly copy and paste this, please feel free to move on to the next one. And I will definitely see you there when we, damn it, that doesn't even fit. All right, I'll put it right there. When we finish solving this Bellman equation, circle it in red. Finish solving this Bellman equation. We're going to take first order conditions, maximize with respect to ct and pi t to find the ct star and pi t star. And we're especially interested in pi t star because this will give us our two-fund theorem. And so we're going to finally prove that in the next video. How exciting. So great. I'll see you there.